Okay, so today we're going to talk about two important theorems. And I guess the more important of the two is the mean value theorem because it's a more generalized statement of the first theorem. So let's start off by talking about the first theorem, which is called Rolle's theorem. So, as far as Rolle's theorem goes, in comparison to intermediate or the mean value theorem, you're going to notice that they have similarities, except the mean value theorem has less conditions that need to be satisfied. So you'll notice, and keep an eye out for this, that there are similarities and differences between Rolle's theorem and the mean value theorem. So let's start off with Rolle's theorem. Rolle's theorem says let f be a function that satisfies the following hypotheses. So once again, it's important to point out that in order for us to be able to use Rolle's theorem, we need these three conditions satisfied. So the first condition is that f is continuous on the closed interval from A to B. Okay, so that's the first condition. And this isn't anything new to us. We've always had to show functions are continuous on closed intervals, which they're important. And then the second condition is f is differentiable on the open interval from A to B. Okay, and then what that does now is we're basically saying that, hey, I don't care if it's differentiable at A and B specifically, but as long as I'm in that interval from A to B, it's differentiable. And then the third condition is if f of A equals to f of B. So what you should notice is that these three conditions pretty much can give us the conclusion, which basically Rolle's theorem says, then there is a number C in the open interval from A to B such that f prime of C equals to 0. So basically, what the conclusion is saying is that if these three conditions are satisfied, then there has to be a place somewhere, an x value between A and B, where the derivative equals to 0. And so notice what this basically means. So there's three conditions. And by the way, one comment I want to make here is when they're saying that there is a number C, there could be more than one. Okay, but what we know is there's at least one place where my derivative equals to 0. So think about this. Here's what this is saying. Think about the conditions. If I have A to B, and what do we notice? The three conditions are what? I need to make sure that f is continuous on the closed interval. So starting from A and ending at B, I need to make sure that this guy is continuous. And then I need to make sure that f is differentiable on the open interval, so it doesn't have any corners or kinks. And I'll show you why, if one of these isn't satisfied, how this statement will fail. And if the y value at A and B are both the same, then we're guaranteed where the derivative will equal to 0 in at least one place. So think of it this way. Imagine if I have my y value at A here, and then what does that mean? My y value at B has to be there as well. So what I need to make sure is this has no cuts or breaks, and it's differentiable. It has no corners or kinks from A to B. So if I draw a function that looks something like this, what do you notice? See, it's continuous on the closed interval, it's differentiable from A to B, and the y values at A and B are the same. And notice how there's actually two places. So in our definition, we're calling these C's. Notice how here the derivative is 0, and this here, the derivative is also 0. So we could also call this maybe c sub 1 and c sub 2. So in this case, in this drawing, I had two possibilities. Remember, we could have 1, 2, 3, or infinitely many places, but Rolle's theorem guarantees this. Now, why are these three conditions important? Well, obviously for continuity, if it's not continuous, I could draw a graph where it has no, basically nowhere where the derivative is 0. But what if I have something like this? Now look, a to b. The y values of a and b are the same. Okay, so condition 3 has been satisfied. Now, condition 1 says make sure it's continuous on the closed interval. And let's see what happens if condition 2 fails. Like, it's not differentiable on the open interval. So this guy, the derivative doesn't exist everywhere. So what if I draw something like this? What do you notice? I have a kink here, so this is not differentiable. Now, notice how there's nowhere on this curve where the derivative equals to 0, okay? But how come this doesn't contradict Rolle's theorem? Because statement 2 fails to exist, because this isn't differentiable on the open interval. It's not differentiable right here, which is causing the problem where the derivative doesn't equal to 0. So Rolle's theorem says, look, if these three conditions are true, we're guaranteed to have a place where the derivative equals to 0, at least one place. There could be more than one, okay? So let's start off with looking at our first example, and then we'll hit the mean value theorem. So for example 1, we want to prove that x cubed plus x minus 1 equals to 0 has exactly one real 0. Okay, so what's our goal? Our goal is to show that this guy has only one x-intercept, okay, and no more than one. So here's the problem. The first thing we need to show is we first need to show that this guy even has an x-intercept, right? How could I show that a function has an x-intercept? And you've done this before. And so let's not focus on exactly one right now. Let's just focus on showing that this guy has at least one. Okay, once we show that, then we'll go ahead and show that, well, it can't have more than one, which means it has exactly one. So if you think about it, what was it that we always used prior to this chapter to show that functions have x-intercepts? And you've definitely done this, and if you already know it, you've probably already answered it by saying it's the intermediate value theorem. So what we first want to use is, we want to first use IVT to show a 0 exists. Okay, so let's do this. What we could say is, since x cubed plus x minus 1 is, and remember, we also need to find an interval where this guy changes from negative to positive. So let's do that now. I know when x is 0, y is negative 1, and when x is 1, y is 2. So let's actually use the interval from 0 to 1. So we could say since x cubed plus x minus 1 is a polynomial function, this implies it's continuous on its domain, which is all reals, which also implies it's continuous on the closed interval from 0 to 1. Okay? So now we could say, notice that f of 0 equals to negative 1, and f of 1 equals to 1. So what could we say? We can say, thus, by the intermediate value theorem, there exists a number c in the interval, open interval from 0 to 1, such that f of c equals to 0. So what have I shown so far? I've shown that there's at least one real 0. Okay? Now, we're not done with this problem, because if you look at this problem, we need to show that it has exactly one real 0. So what do I know? we've shown that a root exists. Now we need to show that we can't have more than one real zero, okay? So here's what we're going to do. Now, to show this has exactly one real zero, we will use a proof by contradiction. So basically, we're going to assume it has more than one. And when we assume it has more than one, we'll assume it has two. Okay, so obviously, if we're assuming it has two, and then something's going to go wrong. And if something goes wrong, then we basically have proven that, hey, it can't have two. So let's just do a quick rundown. I'm going to assume that this function has two real zeros, and something's going to go wrong. So obviously, if it can't have two real zeros, it can't have three, it can't have four, it can't have five, and so on. And since by the IVT, I've shown that it has at least one, then what do I know? We know it has at least one, and it can't have two, then what does that mean? It must have exactly one. Okay, so I hope that what I just said makes sense to you. If it didn't, try to rewind it and replay it and see if that makes sense. Okay, so we can say, suppose there exists two roots, A and B. Okay, so such that, and of course, what do we know? F of A should be 0, which is the same thing as F of B. Okay, so basically, I'm saying if A and B are zeros of my function, then if I plug in A into F, I'll get 0. And if I plug in B into F, I get 0. And of course, we're under the assumption of A does not equal to B. So there are two different roots. Okay? So here's what we could say. Since F is a polynomial function, this implies it's continuous on all reals, which implies it's continuous on the closed interval from A to B. So basically what I'm saying is, if this is continuous everywhere, then it's definitely continuous from A to B. Now look, what are A and B? Those are the x values of where my roots are. So I'm saying clearly this function, since it's a polynomial function, it's continuous everywhere. Therefore, it's continuous from the closed interval from A to B. Okay? So now what we could say is, and notice how this satisfies what? Rolle's first condition, Rolle's theorem's first condition. So you could see I'm trying to put Rolle's theorem to use. Now, what do I need to show? We would also say, notice that f prime of x, which is the derivative, what is the derivative of x cubed plus x minus 1? It's what? 3x squared plus 1, which notice how this is differentiable everywhere, right? If you look at 3x squared plus 1, that'll never be undefined. It exists for every value, which what does that mean? This implies it's differentiable on the open interval from A to B. So what have I just satisfied? I satisfied the second condition, right? Second condition of Rolle's theorem. Now the third condition is also satisfied. Whether you saw it or not, see what are A and B? A and B are roots, which what does that mean? The y value at x equals A should be 0, and the y value at x equals B should also be 0. So we could also say also f of A equals to 0, which equals to f of B, which basically, what did I show? F of A equals to f of B. And I kind of made that comment up here anyway, so I'm kind of like regurgitating it here. So since all three conditions of Rolle's theorem are satisfied, then what could I do? I could say then, by Rolle's theorem, there exists a number C in the interval from A to B such that, and let's call it D because I used C earlier for the IVT. So we'll call it number D in A and B such that f prime of D equals to 0. But here's the problem. Here's where my contradiction is going to come across. I'm claiming that there has to be at least one place where my derivative equals to 0. Well, don't we have the derivative? What we could say is then, but notice that f prime of x, which equals to 3x squared plus 1, if I grab this and set 3x squared plus 1 equal to 0, what does this imply? 3x squared equals to negative 1, which means what? This implies x equals to, if I divide by 3 and take the square root, square root of negative 1 over 3, which notice what's the problem here? This doesn't exist. So actually, that's my contradiction. So what I could say is, so actually what we say is f prime of x in this case will never be 0. Which, what does that mean? Which contradicts our earlier statement. Okay? And why does it contradict our earlier statement? Because we used what? Rolle's theorem. And Rolle's theorem guaranteed right here, if we look at it, Rolle's theorem guaranteed that my derivative will equal to 0. So what's happening here? Does this mean that Rolle's theorem fails to work? And the answer to that is no. There's a problem. Why did the problem we're working with really contradict what Rolle's theorem was saying? Is because we made an assumption that wasn't true. And what was the assumption that we made? The assumption we made is suppose there exist two roots A and B. So what does that mean? This assumption that I made allowed me to use Rolle's theorem, but then Rolle's theorem was contradicted when we tried to find the zeros of our derivative, which means since Rolle's theorem was contradicted, there was an assumption we made earlier that wasn't true, and the assumption we made is that A and B are two zeros of my function. So what does that mean? Basically, if I come back to this page here, which means this implies that f cannot have two zeros, which if it cannot have two zeros and we've shown that one exists, which what does this mean? This implies that f then must have exactly 1 0. And there you have it. So remember, IVT showed us the existence of 1, and then we assumed that it had 2, and we used Rolle's theorem, and we ran into a contradiction, which meant our assumption of 2 real zeros was false. Okay? So with that said, now let's talk about the mean value theorem, and then we'll do one more example, and then that'll basically wrap it up. And I mean, we have a couple more simple theorem and corollary, but let's talk about the mean value theorem. So the mean value theorem says, let f be a function that satisfies the following hypotheses. Okay, so the first condition is f is continuous on the closed interval from A to B. The second condition is f is differentiable on the open interval from A to B. And so notice how there's a lot of similarities with Rolle's theorem. In fact, these first two hypotheses are exactly the same as Rolle's theorem, except for the mean value theorem, we don't have a third hypothesis. So we could say, and so notice how the mean value theorem is a more general statement compared to the Rolle's theorem, because Rolle's theorem is more specific. It's also saying the y values at A and B must be the same. Okay, so here's what the mean value theorem says. Then there is a number C in the open interval from A to B such that f prime of C equals to f of B minus f of A over B minus A. Okay? And, or another way of looking at it is, or some books say this as well, f of B minus f of A equals to f prime of C times B minus A. Now, if you look at these, they're exactly the same thing, right? Because how do I get from here to here? Just multiply both sides by B minus A, and then you get this bottom statement, okay? But more importantly, what is this basically saying? Let's take a look at, let's visually kind of draw something that satisfies these conditions. So what is it that we're saying? We're saying, look, if you have a function that's continuous on the closed interval from A to B, and it's differentiable on the open interval from A to B, and I don't care if the y values at A and B are the same. So I could have maybe something like this. What if kind of my graph looks something like this? Okay, so what is this theorem saying? Basically, it's saying if you find the average rate of change from A to B, because after all, this is the average rate of change, isn't it? So if I find the average rate of change from A to B, which is the slope of this red line, what the mean value theorem basically says is, look, you could find somewhere at least one place, okay, it could be more than one place, but we know that there exists one point on this curve where the slope of the tangent line is the same as the average rate of change, which, of course, for these lines to be parallel, they have to have, or basically what this is saying is, this line and there's a slope of a tangent where they are parallel. And in fact, if you look at this curve, you could pretty much see roughly where that point is, maybe somewhere around here, where when I draw my tangent line, it looks to be parallel with the red line. So basically, this is that number C that we're talking about, where the derivative at C is the same thing as the average rate of change. So the mean value theorem basically says, look, as long as your function is continuous on the closed interval and differentiable on the open interval, then there's at least one place where your derivative at a value is the same as your average rate of change from A to B. Okay, so moving on, let's look at our next theorem. And what does our next theorem say? It says, now this one doesn't have a name. So remember, the ones with names are the important ones. But this one says, look, if f prime of x equals to 0 for all x in the interval from A to B, what could you say? In fact, you could probably make sense of this. Think about what this is saying. If the derivative of f is always 0 from every number between A and B, what must that mean? What kind of a function do I have? Then what must f look like? And if you said, if the slopes of my tangents are always 0, what does that mean? Then my function has to be a horizontal line, or it's a constant. So then this is saying then f is constant on the open interval. Okay, so let's go on to our next corollary, and then we'll do one more example, and that'll basically wrap up this section. Okay, so this corollary says the following. If f prime of x equals to g prime of x for all x in an interval from A to B, then what would you say about f and g? Or what would we say about then f minus g? So what am I saying? If the derivative of f and the derivative of g are the same, then what could we say about the function f and g? And see, if you said that, then f and g must be the same function, you're close, okay? You're not exactly 100% correct, but what we would say is that f minus g is constant on the open interval from A to B. So what am I basically saying? The difference between them will just be a constant, because after all, the derivatives of constants zero out. So for example, just to kind of give you, or let's finish this corollary off and I'll give you an example as to what I mean. So here's what we're saying. That is, if f of x or that is f of x equals to g of x plus some constant, where c is a constant. So think of it this way. If I gave you, so this doesn't necessarily mean, if the derivatives are the same, it doesn't necessarily mean you have the same function. You have similar functions. So an example I could give you is this. Note, let f of x equal to x squared plus 2 and g of x equal to x squared plus 1. And what do you notice? F prime of x equals to 2x, g prime of x equals to 2x. So notice how my derivatives are the same, but these are two different functions. And in fact, when you take the difference, when you say x squared plus 2 minus x squared plus 1, you end up getting what? The difference between these is, if I subtract them, I just get 1. So that's basically what they mean. They're saying, look, if your derivatives are the same, then that means the original functions are similar, but they might just be different in terms of their constants. They may have different constants, okay? So that's what this corollary says. Now, moving on to our last example. We could say, suppose that f of 0 equals to -3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? Okay, so let's kind of be careful here, okay? So here's what we know. Let's make a few comments here, and then we'll figure out that we'll be able to kind of find out what the largest f of 2 can possibly be. So for this example, we could actually put the mean value theorem to use. Okay, now what do I mean by this? Now here's what we know. Since f prime of x exists for all x, what does this imply? Remember, if a function is differentiable, then it's continuous. Remember that statement we had earlier on? So remember, just because the function is continuous, it's not differentiable, but we know that if it's differentiable, then it's continuous. Then what we know is f of x is continuous for all x, which means, and now what am I going to focus on? I'm going to focus on the x values going from 0 to 2. Now, why do I want to use 0 and 2? Because I know what the y value is when x is 0, and I want to figure out what the y value is when x is 2, which then we could say f of x is continuous on the closed interval from 0 to 2. So the first condition of the mean value theorem has been satisfied. Now, the second condition, if you think about it, it's also satisfied. How come? Because that was given to us. We're told that f prime of x exists everywhere, right? And what we know is they even tell us that the value of f prime is always less than or equal to 5. And it's also given f prime x exists everywhere, which means it's f is differentiable From where? From 0 to 2. Okay, so now I could use the mean value theorem. Okay, so let's put the mean value theorem to use now. So we could say, thus, by the mean value theorem, there exists a number c in the interval from 0 to 2 such that f prime of c equals to f of 2 minus f of 0 all over 2 minus 0. Okay, so now let's go forward with this. What's my goal? My goal is to solve for f of 2. And what was given to us? F of 0 was given to us, wasn't it? If I look back here, f of 0 is, it's actually right here, f of 0 is -3. So if I come back to this, I could say, well then, this implies we have what? F prime of c equals to f of 2 minus 3, okay? So, or minus -3, sorry, not minus 3. So it's minus -3 all over 2. So then, here's what I'm going to do. Multiply both sides by 2, and I get 2f prime of c equals to f of 2 plus 3, okay? So from here to here, I just multiply both sides by 2. And then what could I say? I could say, well, my goal is to solve for f of 2. So subtract 3 from both sides. So then what do I get? I get f of 2 equals to 2 times f prime of c minus 3. Okay, now notice when you're looking at this, you're saying, wait a minute, I need to figure out what's the largest f of 2 can be. But what was the fact that we were given about f prime of x? In fact, isn't c an x value? So let me go back to this problem, and let's read the directions again real quick. What were we saying here? Suppose that f of 0 is -3, and f prime of x is always less than or equal to 5 for all values of x. So what does that mean? If I come back to this, what we know here is that, let me make a side note here, f prime of c is what? Less than or equal to 5. Okay, that's a fact. So what do I know here? We're saying that f of 2 equals to 2 times f prime of c minus 3. And since f prime of c is less than or equal to 5, and this was given to us, this was a fact, then I could say what? Then this guy is less than or equal to 2 times 5 minus 3. Because look, if f prime of c is less than 5, then 2 times f prime of c minus 3 will be less than or equal to 2 times 5 minus 3. Okay, so then once you make this connection, this is what allows me to introduce this inequality, which, what does this become? 2 times 5 is 10 minus 3, which is 7. So what is it that we're claiming? We're claiming f of 2 is less than or equal to 7. So in other words, this implies the largest f of 2 can be is 7. Okay, and so that basically finishes up this example. So remember, the mean value theorem was key in this problem because the limited information I was given, I was able to solve out for this. Okay, so that wraps up this section. And once again, if you have any questions on Monday, feel free to ask, or next time I see you, feel free to ask about any questions you may have regarding this. Okay.